this lecture, we will be talking about learning in math and science. What is unique about learning in math and science domains is that they combine a focus on what, the facts we know about the world within various science and math domains, with a focus on a process, a kind of how, that people can use to identify and to solve new problems within science and math domains. Like storytelling, once we learn the skills within these domains, we're able to also use those skills to generate and acquire more knowledge. On the one hand, the learning of what, like acquiring the multiplication times tables or memorizing the periodic table of elements in chemistry, that has a lot in common with information processing approaches and verbal learning research. What I mean by that is that using elaborative encoding strategies and repeatedly testing yourself are going to be good strategies for acquiring those facts. And if you think about it, especially for the multiplication times tables, that is how schools help kids learn those parts of math and science. But how do we learn a process of problem solving within these fields? Today, we'll first look at how people learn strategies in math and physics, and then we'll move out to the broader issue of discovery or inquiry-based approaches to learning in math and sciences. This has been a fairly hot topic within education for the last decades. Strategy acquisition in math has been studied by a variety of researchers, but the work of Siegler and his group actually stands out in this regard. They've looked at a lot of different kinds of problems in math. And some of their work looks, for example, at how children learn what's called the counting on strategy for solving addition problems. Now, when they begin adding, young children use their fingers and they use counting to solve addition problems. But this strategy falls apart when you don't have enough fingers. So as soon as you're trying to do something like add 8 and 8, you run into trouble. Eventually, kids learn that they can begin counting from the larger of the two numbers in the problem. They can start with 8 and go 9, 10, 11, 12, 13, 14, 15, 16. That expands their counting options significantly, and that strategy is called adding on. Siegler's work examines how children learn strategies like adding or counting on, and more importantly, how children learn to use them well. Now you might be thinking, duh, you tell the kid what to do, and then he or she practices. But oddly, it's not always so simple. And just to give you one example of this, I've been attempting to show my 5-year-old daughter the counting on strategy for some time now. Now, she understands the strategy when I show it to her. It makes sense to her, but she finds it difficult to figure out how to start it when she's on her own, and she hasn't adopted it herself yet. As I'm giving this lecture, I've demonstrated the strategy to her about 3 times, and I've had no apparent success so far. So let's consider a different type of math problem. There's a type of math problem called class inclusion, and class inclusion problems involve reasoning about wholes and parts of wholes. Let me give you an example problem. John has 3 cats and 4 dogs. Does John have more dogs or more animals? Now, you can solve this by counting, which is an empirical strategy, or you can solve it by reasoning about sets and subsets, reasoning about class inclusion. That's what we would call a logical strategy. Now, if you choose the logical strategy here, you don't even need to bother with the numbers. You know that because both cats and dogs are animals, John has to have more animals than dogs. Now, this is a pretty easy example, and adults can continue to have trouble with class inclusion problems that are sophisticated and complicated, but most of us can acquire a basic understanding of class inclusion problems in early to mid-childhood, by the end of the elementary school years, say by age 10 or so. But earlier on, we do have trouble. 5-year-olds, for instance, when presented with this kind of problem, respond that there are more dogs, because there are more dogs than cats, and that confuses them. Now, as I said, it's not till age 9 or 10 that the majority of children in the United States correctly respond to a standard class inclusion problem of this type. Knowing that there are age differences, though, doesn't really explain how kids come to understand these problems and learn to solve them correctly. And to do that, researchers need to use what's called a microgenetic research design. Now, microgenetic designs make a lot of observations of people learning something, and they do that over a short period of time. So generally, studies like this show that right before people discover a new strategy or a new way to solve a kind of problem, their performance gets more variable. So a child who's about to discover a logical way of solving class inclusions might begin to get some problems right and others wrong shortly before he or she first gets to that logical strategy. Often, discovering a new strategy is followed with a period in which the new strategy coexists with older ones. So even when kids know the advantages of the new strategy, remember that I mentioned my daughter understands that the new strategy works for bigger problems. But even when kids understand that, they're sometimes slow to fully adopt the new strategy. Variability across different kids is also pretty high, and what that means is different children's acquisition of strategies looks different, happens at different times in the process, and the acquisition of strategies doesn't always look all that orderly, the way we might imagine it in the abstract. Now, this isn't always the case. Sometimes when kids get a strategy, it's like an aha moment, and they just get it, and they go with that. And that happens to be the case for class inclusion, and I'm going to illustrate this with an example study. In this particular study, Siegler and his collaborator Svetina were interested in children's learning of logical versus empirical strategies for class inclusion. Now remember, empirical strategies involve doing the counting and comparison of the relevant numbers, and logical strategies involve simply reasoning about the groups, saying they're all animals, therefore more animals. Now, as we saw in the example, a logical strategy is more efficient. You don't have to do any addition. So in this study, 5-year-old children saw 30 different class inclusion problems like the one I just told you about. And they saw them on 3 separate occasions. So on each occasion, the kids would see 10 problems. And the researchers randomly divided the kids into 4 different groups. Now, one group received explanations about why they were getting it wrong. And remember, these are 5-year-olds, and so they get the problems wrong. So one group received explanations that were empirical explanations. The experimenter would say, no, that's wrong. The correct answer is more animals. And then the experimenter would show the child the exact number of animals there were versus how many dogs there were by actually counting it out for the child. So the experimenter would explain using an empirical strategy. Now, a second group got logical explanations about their wrong answers. The experimenter would talk about how there had to be more animals than dogs because all of the pets were animals, but only some of the pets were dogs. A third group received both types of explanations in response to their wrong answers. And a fourth group simply were told whether they had the right or wrong answer, but they weren't given any explanation at all about why. Now, if you looked at the results of this study, what you would see is that by the 3rd session, children who had received logical explanations, whether or not they had also seen an empirical explanation, were successfully solving 8 out of the 10 problems. Children who were given no explanations were still only solving about 40% of the problems correctly, and that's about the same as where they were when they started. And kids who got empirical explanations, where the experimenter showed them how to count, also didn't get much better. The second thing you can see when you look at the findings here is that performance didn't get better gradually. Rather, as soon as kids discovered how to use the logical strategy and started using it, their performance skyrocketed. So in this case, learning to solve the problems is really about learning the best strategy for doing so. Now, I wanted to tell you about this study in particular for a reason, because there was a different part of the study that makes it, for me, one of the coolest studies that I've read in this area. Siegler and Svetina also checked how performance on class inclusion problems changed with age in a different group of kids. And in that group of kids, the children ranged from 5 to 10 years of age. Now, over that time frame, performance on the class inclusion problems goes from about 30 to 40% correct in the 5-year-olds to 90% correct in the 10-year-olds. So, what Siegler and Svetina did with 3 sessions of 10 class inclusion problems each, plus some explanations, was to take 5-year-olds and teach them to perform like 10-year-olds in the space of 30 problems. What this means is solving class inclusion problems is something people learn to do. It doesn't require some kind of special maturation, special developmental changes that only happen by the age of 10. The other thing that's cool about this study is that it shows class inclusion problems can be learned really fast, given a few conditions. One of which is just having a lot of opportunities kind of massed together to try out the problems, getting some feedback about whether we're trying the problems and getting them right or getting them wrong, and getting a good explanation about why the wrong answer is wrong, and an explanation that specifically highlights the correct, most efficient solution strategy. We've hinted around about the idea of self-explanations before, as little Emily worked out scripts in her crib through telling stories, and when we discussed adults explaining the potlatch ceremony to themselves in order to learn the potlatch script. In her work on science learning, Michelin Chi has noted that self-explanations play a critical role in determining how well people learn aspects of physics and other sciences. Now, to understand where she's coming from, you need to consider that one feature of science is the role played by models of how things work. So to understand many areas of science is to understand something about the models that exist in those areas and the way those models are supported by the data scientists have collected. Now, Chi's work focuses on how people learn and update their models about how something works, with a few key assumptions. Now, first, they assume everyone brings to the table an existing model, say, of how electricity works, although that existing model may be flawed. For example, it's common for people's naive models of gravity to include the idea that differently weighted objects will fall to Earth at different speeds. And it's also not unusual for a novice model of electricity to be focused on the idea that electricity is a substance rather than a process. And it's common for novice models of the circulatory system to be inaccurate about how blood is oxygenated, or to be mistaken about the role of the lungs in oxygenating blood. So for Chi, science learning is a process of changing students' existing models to more accurate ones based on what students read or their experiences that give them additional facts. As a science teacher, you can ask, how can we do this better? Or as a science learner, you can say, how can I do a better job changing or modifying a naive model towards one that's going to be more accurate, more consistent with what scientists know? Chi and her collaborators focus on self-explanations as a very important factor in that process. What's a self-explanation? Well, a self-explanation is the occasion where you talk yourself through a difficult problem or a difficult text. You explain to yourself what you do know, you try to connect what you're reading about to related knowledge, and you try to identify what it is about the text that you're not really understanding yet. This process should sound a lot like what we were earlier referring to as elaborative encoding or deeper processing, but it has a bit of a twist. It's oriented towards grappling with difficult to understand material and towards making sense of that material, towards making an accurate model. Now, people sometimes engage in self-explanation spontaneously, but they can also be instructed to do so, particularly beginning in middle childhood around age 8 or so. And if you instruct people to engage in self-explanations, the result is better problem solving and better comprehension of texts. Now, of course, when you ask people to talk to themselves while they're working on learning something, they say many things, and some of these things don't count as self-explanations. People also say things like, I'm confused, I'm feeling exhausted. These don't concern the material to be learned directly, and they're not linked to better learning at all. So it's not just anything you say to yourself while you're trying to learn, it's explaining things to yourself as you're trying to learn. It's focused on the content. Self-explanations include things like restating, summarizing what's in the problem or the text, and other ways of bringing together what's in the text with what the person already knows. Finally, some of what people say are what she and colleagues call self-explaining inferences, and these are particularly good. These are statements that go beyond what's in the text and make inferences about it. These are statements that say, oh, so if blood then goes to the lungs, it has to come back through the heart in order to get pumped out to the body. Statements like that are associated with increased learning, and more importantly, they're associated with changes in students' models from the naive models that are actually inconsistent with scientific findings to the models that are more supported by the available data. Now, Sigler and Chi's findings really highlight this process of explanation in the learning of strategies and in the updating of mental models. And they also point to the way that people can do quite well at self-directed learning and self-directed acquisition of new knowledge, as long as they're given a lot of exposure to problems and a little support in the way of feedback and explanations. So, if self-explanations and trying out strategies is so important to how we learn in a problem-solving domain, like math and science, then one of the most obvious questions to ask is, are there ways of teaching that kind of material that are likely to promote those activities, or likely to promote people explaining things to themselves and trying out strategies? Well, since the 1950s, educators, researchers, and even parents have proposed movements in favor of what is called discovery-based learning. Now, discovery-based learning means many things, but specifically, it involves the notion that the learner should be the center of action and that the learner should be engaged actively in trying things out and making his or her own discoveries about the material to be learned. This type of learning is viewed as being most effective in the long term, and it's also viewed as good because the idea is that this kind of learning really preserves the learner's own motivation. That is, it's exciting and engaging to learn by doing and trying things out yourself. And within this kind of area and within this kind of thinking, discovery-based learning is contrasted with explicit teaching or traditional instruction. Explicit teaching and traditional instruction are described as focused on an authority figure, often a teacher, and the authority figure presents material for the student to learn and directs how things will go, what's going to be covered when, how students should understand what they're hearing. Now, proponents of discovery-based learning argue that traditional instruction leaves students passive and unmotivated. Of course, as is always the case when you have two extremes, there is a middle ground, and a middle ground between these two extremes emphasizes what's called guided discovery or elicited self-explanations. And you may be thinking, and you'd be right, both the work of Sigler and Chi that we just discussed would point towards this middle ground as the ideal. And in fact, entire established and successful educational systems have been built on these kinds of principles. Montessori education is probably one of the best known examples, and it's probably best conceived of as involving guided discovery. On the surface, discovery learning sounds great. It has a lot of catchwords that we really like: engaged, motivated, discovery, inquiry. But before we get too enthused, we need to think about some of its potential pitfalls. First, it is labor-intensive, and it can't, particularly for younger kids, be done with large class sizes. A teacher can't provide individualized feedback and individually tailored explanations for a class of 30 or 40 children. Another issue with discovery-based learning is it can be costly in material terms. That is, kids need materials that they can work with for discovery-based learning, again, especially when they're younger. Now, computer-aided instruction may change that in that it makes it less expensive to create situations for kids to explore. Now, a third problem is that it may take a naive student a very long time to discover things that are foundational, things that we've known for so long and that we need to take for granted before we can move to the next step in an area. And because of that, discovery-based learning could slow down the educational process. And finally, developmental psychologists would say you really need to think about the age at which we could be sure kids could systematically engage in inquiry-based learning rather than simply do a lot of disorganized and random actions with their materials that end up not teaching them very much at all. So how does research suggest that this type of learning stacks up? Well, there's been a great deal of work in this area over the last several decades. It's been published in many of the major journals in educational psychology. And when we have that fortunate circumstance as scientists, one of the best ways to make sense of everything is called a meta-analysis. A meta-analysis is a technique for synthesizing findings from many different studies in order to be able to draw some general conclusion. And when there's a large body of research findings, it represents a way to pull together all the findings. Because of that, it's considered much more reliable and trustworthy than a single individual study. It's kind of a picture of everything we know. To do a meta-analysis, researchers first collect all the individual study reports. Then, for each study, something called an effect size is computed. An effect size represents the difference between different groups in the study. In our present case, that would mean the difference in how students do with discovery-based learning and traditional instruction. Once each study gives us an effect size, we put the effect sizes together across all the studies, and we can use some statistical tests to say whether that effect size in general across all the studies is different than 0. An effect size of 0 would mean there's no difference between the two types of instruction. It doesn't matter for student learning whether they have discovery-based or traditional instruction. Now, beyond just that, beyond just asking, is there a difference and what is the difference, we can also look at what factors from different studies look like they're related to the size of the difference. We can look at factors like the age of the people who are learning. For example, we can ask, does discovery-based learning work differently for children than adolescents, than adults, and so on. A recent meta-analysis of about 108 studies of discovery-based learning shows us that if we compare what I'm going to call purer, or you can think of it as more extreme, forms of discovery-based learning, if we compare those to explicit traditional instruction, explicit instruction is more effective for learning outcomes in many domains, and that includes math and science domains. This is also true across childhood and adulthood. And the advantage of explicit traditional instruction is particularly strong for adolescents as compared to adults. In adulthood, the two forms of instruction are not so different. This is disappointing news for that positive, exciting sound of discovery-based learning. But the news isn't all bad. The same meta-analysis also looked at enhanced discovery learning, which is something like the kind of middle ground approach that I mentioned above, and it's the kind of approach that would be consistent with Siegler's findings and with Chi's findings on self-explanations. In that comparison, two forms of kind of moderate discovery learning, guided discovery, were better than other forms of instruction. They were better than pure discovery learning, and they were better than traditional instruction. And this was especially true for adults and adolescents. Now, those better forms of instruction are elicited explanations. That's exactly like Chi's work, where instructors get students to generate self-explanations, and guided discovery, which involves an adult or an expert providing informative, meaningful feedback and structure for students' own discovery-based learning. And that's quite a bit more like Siegler's studies. One feature that all forms of discovery-based learning have in common, whether they are the pure and apparently less effective form, or the more moderate and highly effective form, is a focus on solving problems rather than on hearing a lecture. Problem-based learning is another kind of approach that's used to teach areas where people will need to engage in a reasoning process, a kind of how, rather than to simply recall facts. Arenas where problem-based learning has been used include ethics, where people are presented with ethical dilemmas and asked to reason about how they can be resolved. Medical school, in particular with issues of diagnosis, medical students are presented with symptoms and asked to engage in the process of diagnosing. In business school, students read case studies about different businesses facing different kinds of dilemmas, and they think about how the business might strategically respond to those dilemmas, and then they're often able to look at how the business did respond and what the consequences were. And in science and math, Problem-based learning is effective in many of these cases, and what problem-based learning consists of is really giving people a problem to solve. And again, as with what we just discussed, problem-based learning, just like discovery-oriented learning, is best when it is scaffolded or assisted by people with greater expertise. Evaluations of problem-based learning versus more traditional approaches in those fields also show that people like it more. They're more motivated by it. Sometimes, however, the outcomes are kind of mixed, and that again is also a little bit like what we saw with the meta-analysis. Problem-based learning never seems to hurt people, and that's different than the meta-analysis we discussed. In some cases, people actually may be better at thinking through procedures when they've been engaged in problem-based learning. And certainly people feel more confident in some problem-based learning environments. They feel more certain of their abilities to go through the real aspects of their jobs. Now, finally, while learning in science, math, and many other fields can be viewed as both learning what and learning how, or the process of solving problems, the sciences are an arena where people also need to learn how to identify or to find a good problem. A good problem in science is one that isn't already resolved, but it's one we can resolve or we can answer using available scientific methods and techniques. And usually a good problem also needs to be one that we think is important to resolve. So a final question in this area could be, how do scientists learn to identify good problems in their fields? Well, despite the ironic fact that most graduate training of scientists in various fields of science is actually aimed at teaching people to both identify and to solve important scientific problems, remarkably little is known about how people learn to do so. But we can draw from work on creativity and innovation to make some guesses about how people learn to find problems. Creativity research, based on examining the biographies of eminent individuals like Beethoven, for example, suggests that to produce great works, and in science that would be great questions, people first need to have a relatively high level of expertise in their field. They need to know what is known in their field. That expertise gives people a foundation from which they can create novel and creative works, and this happens for at least two reasons. First, without a basic foundational knowledge of the area, it's very hard to avoid repeating old ideas or concepts. So scientists who don't have a foundational knowledge ask questions that we already know the answers to. Now, second, though, that foundation of expertise gives people a set of rules and assumptions within which creative work can emerge, or really important new questions. So within a given area of science, for example, there are things we know a lot about. And any new question will build on the understanding of those phenomena that we currently have. But as someone's knowledge develops, he or she has a greater chance of being able to notice an area where we don't know enough, or where there's some conflicting findings, and it would be good to figure out what's really going on. Finally, because science and many other endeavors involves having guesses about how your data will look, and then testing your expectations or hypotheses against the data you actually get, we learn a lot in science from having our expectations violated. In other words, we learn a lot from being wrong, just like Siegler's 5-year-olds. So being able to analyze and learn from cases where our findings didn't come out as we expected may be one of the most important sources of finding new questions in science. And again, that really brings us right back to those 5-year-olds learning class inclusion problems. Failing and having failures explained was a crucial way that they made it to the next level. Now, in summing up, research on learning in math and science emphasizes a body of knowledge, a what, and a process for solving problems and generating additional knowledge, a how. Because of this latter component, the how, people learn math and science partly by solving problems. And so some of the important questions in the area have really been about how people learn more effective and more broadly applicable problem-solving strategies, and how they're able to change their models or understandings of something from less accurate models to more accurate models. And as we've seen in this lecture, as people acquire new strategies, they may initially become more variable in their performance before they settle on the newer and better strategy. People also need clear, explanatory feedback about their performance for this type of learning. And when they engage in self-explanations about what they're learning, that really helps them move from incorrect to more accurate models. In fact, the process of explaining errors to ourselves that can lead to real learning, explaining errors is something like the way telling stories helps us figure out scripts for events in the world, but it applies more particularly to math and science. In explaining errors, people consider their own answer to the math problem versus the correct answer, or they consider what they expected or believed to be true about, say, electricity, and what turns out to be true. Now, this is the core of theory testing in science more broadly, contrasting our expectations with our actual observations. And as it happens, some approaches to learning view all learning as being a kind of theory testing. And the argument is that what people do when they learn is they develop and express expectations, and then they look at whether their expectations prove to be accurate. Is this a good way to understand learning? Next lecture, we'll see how that way of thinking about learning, the idea of learning as theory testing, looks. We'll ask how well this idea of theory testing does at explaining what we do know about learning. And finally, we'll discuss whether theory testing itself is something we have to learn over time how to do.